So our second instance is going to be about exceptions, or at least a basic style of exceptions. In fact, this was our introductory example because it's one of the simplest, again, patterns that we can imagine. We have a box or we have an extra flag that says, whoa, an exception has been raised. And this is what our exceptions are going to be, a single possible error value. Of course, in real life, in I don't know, Java, in C, in pretty much any language with ML, language with exception, you can have several exceptions, and then you can catch them individually. So based on their types, right? Okay, is this a null pointer exception? Then you do something. Is this such and such? And you do something else to recover. So we're going to have only one value. I think more values might come in the exercises or homeworks or even exams. I think the exam of last year had more fancy exception types. So these are always good questions. Yeah, we've seen that before, option pure, option bind. So I'm not going to dwell on this. Here you have the registration of option, which well, it's straightforward, except that we need to do a case distinction here, right? So we have this operator here. Again, if we have to prove something like this, I mean, unless we can work things out in our heads, I mean, typically we first want to unfold this operator, which is, the operator we've just registered as bind here. We want to unfold this definition to have this one instead, right? So let's try to do that. And I don't know why it's so slow, but right. And now we see a bit clearer. But unfortunately, we have option bind of M, right? And what do we call M instead of MA? That would be a better name, I think. It's hard to achieve uniform names. You think you've got them all, and there's still a couple working around. Okay. So that's where we do a case distinction, because bind is defined by a case distinction. Here you see you have the non-case and the some case, right? So that when you reason about a function, you want to follow its definition. So here we're going to do a case distinction as well. And then you have bind non, blah, blah. Okay, that all looks a bit boring. You give it to REFL and it takes care of it. And if not, then we can try again to simplify ourselves and see, okay, where does it lead, and so on. But once we're done with the proof, we can be machos and remove these needless steps if we want. It's really as you want. Again, if you add more steps than necessary, I'm not even going to comment on that in the homework. And there are legitimate reasons for doing this also in production code, in real formalization. So it's really a matter of taste, something that you develop over time, which tells you, okay, how much detail should I keep in my proof, and what is interesting and what is boring. And everything that's boring, you try to automate. And everything that's interesting, you try to do one step at a time, so people looking at it later can, see the interesting proof unfold. Okay, ASOC is the same idea. Yeah. Now we'll provide two more operations. We provide a throw operation, so that at any point you can, throw none. That's convenient. And catch takes two monads, or two options in this case, and returns an option. The idea is that if you have a failure in your first program, then you try to execute the second program, right? So in Java, you'd have something like, is in C, try something, catch something else. And suppose this is, this is block 1, and this is block 2. So basically, it would try to execute block 1. If there's an exception, it would do block 2 instead. If there's no exception, it would do block 1. And this is exactly what we're achieving here. So if there's an exception here, then we return the second guy here. And if there's no exception, then we just return the first argument unchanged. And that behavior is called or else in Lean. So there's an or else type class, which provides an or else operator with this syntax here. So we're going to register or option catch as an or else, and then we'll be able to write things like you know, MA1 or else MA2, where this could also be a do block typically, right? And this would also be a do block. And so it's a bit like try this, catch, and then you recover with that. You see, we're simulating what we can already do in you know, other languages without extending the language, without adding complicated constructs to it, without complicating the compilers, the interpreters, the documentation, and so on. All we have to do is, you know, embrace the you know, scary word monad, and then everything is fine.